Welcome to the webinar on strain measurement for sheet metal testing and eliminating R-value variability. Thank you so much for being here. I'm Nick Erickson, your host for this webinar. Today, I'm joined by Dan Raynor, product manager for all of Instron's strain measurement products. Dan's history with Instron stretches back 16 years as of last Thursday. Congrats, Dan. That was when he started off as an applications engineer within our static testing division before moving to a field-based role with our dynamic testing division, and has now come back to the world of static testing with a primary focus on strain and extensometers. Quick fun fact about Dan is that he has a 1967 Pontiac GTO that he has primed for hot rodding for his LinkedIn profile. And he's also a fantastic, he is fantastic at diagnosing car issues, even when folks like me do a poor job of explaining the noise my engine is making. It's truly a gift. Dan will be providing an overview of formability testing for various sheet metals and the challenges in measuring strain on these materials. He's also going to be discussing a new advanced feature that can be added to our advanced video extensometer that can eliminate R-value variability commonly seen in sheet metal testing. We're also joined by Matt Spirett and Charlie Pryor, members of our applications team. These two will be keeping an eye on questions while Dan is presenting. So I just want to encourage you to send in any relevant questions that come to mind as we go along. We're going to address those at the end. So with that said, I'm going to turn things over to Dan.
Thanks very much, Nick. Good morning, everyone. I hope you're seeing the correct screen of my slides. So as Nick mentioned, we're going to be talking about strain measurement for sheet metal testing and eliminating R-value variability. And just so you can put a face with the names, I'm Dan Raynor on the left. We also have Matt Spirett, Charlie Pryor, and Nick Erickson. And kind of the agenda for today, as many of you know, this topic could probably cover hours, if not days of information, but we're going to try and keep the presentation to a manageable length. So we're going to focus on strain measurement and R-value primarily. And of course, if you want to learn more about anything you see today or any other topics, please don't hesitate to reach out to us through the website or your local Instron sales and service engineers. I believe you also receive a survey at the end of this presentation where you can let us know if there's any other topics you'd like to see webinars on. So the agenda will cover some of the industries where we see driving change in sheet metals, of course, challenges with sheet metal testing. We'll focus on the formability, so R&N values, challenges in measuring transverse strain specifically. Of course, some recent changes to the ISO 10113 standard for R-value. We're going to talk about the new average 32 capability, and then of course some Q&A time. So we see these three industries primarily driving the change in the needs of metals, among other industries. And of course, these challenges create, the needs of these industries create challenges in manufacturing newer materials, as well as changes to the test standards. So you've got automotive, consumer products, and aerospace. As an example, the automotive industry pre-2020 was probably the fastest growing for sheet metals, primarily due to the advances for lightweighting and electric vehicles. So when they look at reducing emissions, they're looking at stronger materials so they can use less of it and save weight. Of course, there's competition from composite materials to replace metals. Formability, however, is very important and is a differentiator for metals. And then, of course, the increased strength can decrease formability in some cases. Use of aluminum kind of taking over some areas where steel primarily had been used. And of course, using aluminum in new applications or new locations will increase testing scrutiny as well. And all the normal growth in the industry, of course, there's increased production, which requires more testing. So these stronger materials present their own set of challenges, increased load requirement. These are kind of things to perhaps think about or consider as you see your needs changing. Is your current machine capable of the higher forces? And that could be either the frame itself or the grip capacity, You might see increased wear on your system, if you're testing it at 100% every test, all day long. And then, of course, do you need higher force capacity? Gripping issues, primarily, are you seeing, do you have to increase the clamping pressure? Are you seeing slippage, which can be a sign of draw faces being worn, which only leads to more specimen slippage, which only increases the draw face wear. So it never fixes itself. But a different draw face design might be available, or you may need different grip design entirely. So hydraulic side acting instead of mechanical wedge. And of course, some of the specimens exhibit violent specimen failures, in which case, if you leave your extensometer on through failure, you might see damage to it, or especially just increased wear on the knife edges. And same idea here, if the knife edges wear, you could see specimens, extensometer slipping on the specimen, which can affect your readings as well. And then, of course, reduced formability due to the higher strength. If you've always been just above your minimum spec for your R&N values, the reduced formability could make it even more difficult for you. So it really shows that you need to accurately and repeatedly be able to measure your R&N values. And that can certainly be done with the proper equipment. So getting on to formability challenges, certainly metals formability is a unique selling point versus composite materials. Some questions I would think about are, is the formability properties important to you? Calculating R&N values requires extensometry, as I'm sure many of you are aware. Some other questions would be, do you know the yielding behavior of your materials? Only because the test machine can be, the test can be, I guess the throughput can be increased by changing or required by setting the control modes of your test dependent upon the yielding type of your material. And the standards go on to talk about that as well. And then, of course, are you testing more and more specimens? And do you have time for retesting? And of course, there's a lot of ways that we can semi-automate or even fully automate systems, whether that's more hydraulic grips as opposed to manual grips, more automated means of extensometry, or even, again, full automation, and as well as making changes in the software so there's less user input required. Looking at end value, which is typically a pretty important one. It tells a lot about your material. It's the sheet metal's response to cold working. And you can see that as a measure of the increase in strength due to plastic deformation. So it kind of defines the difference in stress values between yield and UTS, as displayed in that graph you see there. And it requires axial strain to be measured. So sheet metal with a higher end value exhibits a greater increase in strength with minimal elongation. And now we're going to focus on R value, which is probably the greater topic of this presentation. It is the plastic strain ratio, and it's the ability to resist thinning or thickening when subjected to a tensile or compressive force. It can be difficult to measure the thickness change of a specimen that is already thin to begin with. So the standards talk about using length and width changes to calculate R value. So that does require axial and transverse strains to be measured. The image you see on the left side is our AutoX 750. That's actually our AutoX biax. It's measuring the axial strain as well as the transverse strain. And this is the transverse arm, or head as we call it, measuring a single point in the middle of the specimen. Some images of the current extensometers that we offer. So for end value, you have axial strain capability is all that's required. We have our automatic extensometer, the AutoX 750. We have manual clip-on extensometers. And then, of course, we have our AVE2, the video extensometer that would track marks on the specimen, so it's non-contacting. For R value, we can add the transverse capability to the AutoX 750 for AutoX biax. We do have manual clip-on transverse. This one is specifically designed for sheet metal and averages 2 different measurements. And then, of course, you can measure axial with the AVE2 as well. Transverse with the AVE2 as well. So to talk a little bit more about the extensometer solution, transverse extensometers pretty much must be used with axial. Majority of them have a single line of contact, so you're providing transverse strain at one location. Of course, as I mentioned, some extensometers can provide average transverse strain from 2 locations. Most material has uniform elongation, so the strain distribution is homogeneous up to ultimate tensile strength. And so in most cases, single point transverse is typically sufficient. But of course, for the most sensitive result, such as R value, small errors can equate to large changes in your R value. And one of the major influencing effects would be the PLC effect. So for those that don't know, that is the Poitevin-Le Chatelier effect. So materials that exhibit this PLC effect, which is primarily discontinuous yielding materials, show waves of localized strain. We can this has been put into 3 different categories. So you've got type A, which shows bands of strain or Luder banding, starting typically from one end, propagating across the specimen, and then back down through the gauge length. So that typically causes some noise in the data. Type B would have these steps occur at different distances throughout the specimen, so it typically ends up creating slightly more noisy data. And then type C, where the bands can occur randomly, and it has the most significant noise and really creating this sawtooth pattern. Now, the effect this has on axial strain isn't as critical because your axial gauge length typically consumes almost the entire narrow region of the specimen. So therefore, it kind of gets averaged out in the middle, across the entire gauge length. Using our DIC capability with our DIC replay software, we kind of have some screenshots here of different points of the test. So you can see where the banding kind of starts, and this would kind of propagate throughout the specimen. But on the next page, transverse strain is perhaps a little more critical of PLC effect. So what this chart shows is the right y-axis is the specimen width, and it's versus tensile strain. So we've got kind of this step pattern, and what's that showing, if I start this video, is that this is the digital image correlation video of a test running, and it kind of shows where you can see these waves propagating at different points of the specimen. And if you can imagine a single point of transverse strain being measured, each time one of those waves passes the point of measurement, you can get a step. So it's kind of a step change in the width. And the problem there is that if you go to measure, R value at any specific point, say 10%, if you happen to fall on one side of the step or the other, that'll significantly affect the variability of your results. And it's really just luck of the draw, depending on where that happens and when. So what we did here is we actually ran a specimen with multiple transverse measurements along the axial gauge length from edge to edge of the specimen. And so what we're seeing is that all these curves are, you can see they're kind of similar. They're not all happening at the same time. And that's the wave propagating past the different points. The problem is that you can see there's a huge variability. And if I was to look at, say, R20, one result would be 0.85 and another would be 0.45. So that's a huge variability. And what we can do is we kind of average these values. So you kind of get this heavy red line through the middle, and it's significantly more consistent. So this also follows on with some of the new guidance from the ISO 10113 standard for 2020. So this is the appendix, which talks about R value determination and sources of error. They specifically talk about single line versus multiple line measurements and the location of extensometer gauge length, and specifically non-homogeneous deformation of the test piece related to the PLC effect. And in the method itself, they use some strong wording. So besides using the regression method for inhomogeneous behavior, as well as the piece shall be measured with an accuracy and the minimum of 3 points evenly distributed along the gauge length, including one close to the position at each end of the gauge length. And of course, the average value of these reductions in width measurements shall be used in calculating the plastic strain ratio. So essentially, it's recommending, or strongly recommending, that the average transverse strain for materials which display the PLC effect. So we have a solution now that builds on our video extensometer. We call it Average 32. It is an advanced feature of the AVE2. It utilizes markless edge detection technology, and it simultaneously measures transverse strain at 32 locations along the axial gauge length, and those are then averaged into one smooth and repeatable value. So it can be added to the existing AVE2. There's no transverse marks needed. It measures from edge to edge. There's 32 gauge widths, and it averages all 32 values in real time, which is average 32. So this is an artist rendering, so to speak. Again, you don't need to put transverse marks on there. Those two dots you see at the top and bottom are the axial gauge length, and it uses those as endpoints to define where those 32 gauge widths will be created in the software. And so this is specifically designed to measure the R value of sheet metal by following the ISO and ASTM and JIS standards. So just in case some of you, it looked like at least half of you are familiar with video extensometry, our AVE2 advanced video, you can learn more about this on Instron.com. It is non-contacting strain measurement. You can do axial and transverse. Accuracy is down to plus or minus 1 micron. The largest field of view available is about 840 millimeters. Some other key features, there's patented lighting and thermal airflow management, so it's not affected by lighting conditions in the lab. Interchangeable lenses, which allows for multiple field of views. There's a very simple calibration wizard. The 490 images per second to calculate strain in real time. All the image processing is done on board the AVE2 itself, and so it can send a digital signal directly to the frame controller. And there's also an analog signal available if you want to use it on non-Instron systems. And so that red box is the AVE2 that you see pictured here. There are some patent pending technologies for this average 32 feature. So there's an industry's first dual use lighting system. The idea here is that we're using the existing LED lighting on the AVE2 to light up the front and the rear of the specimen. There's a reflective back screen that gets installed, and then it's simply, it's passive, so there's nothing to plug in, and it also is designed to reflect it back to the specimen and not to the user. So there's no eye strain just working around it. It's very important. We've created a thickness correction algorithm, which eliminates the need to recalibrate or reposition the camera for different specimen thicknesses. It also eliminates the need for costly telecentric lenses that typically limit the field of view and the total elongation. And we've also greatly improved our contrast compensation routine, which provides for robust tracking of marks and the specimen edges. Sorry, it looks like the slides are catching up. Okay, so just wanted to show you roughly what the user interface looks like from our Blue Hill Universal software. This was actually taken from our ASTM E8 video on YouTube on the Instron channel. So the red boxes over here show what the AVE2 is tracking. That green box is what we call in the area of interest, so you can tell it where to look or where not to look. So if you've got a shiny reflection in the background or another white spot on your test fixture, perhaps, you can simply ignore it. The new average 32 feature, again, uses same idea. Show the red boxes show you where it's tracking. So it finds the axial marks, and then it creates these transverse edges between those marks. So it uses those as the endpoints. You will notice that we can, we've got a specimen here with a white background, and that's because we're illuminating the back from the back of the specimen as well, so we can get a nice contrast to those edges. On the left side, we do not light the back of the specimen typically, and our cross-polarization routine between the lighting and the lens allows the specimen to simply vanish into the background. So all you see is white marks floating in space, which gives us excellent contrast. So some testing we did. This graph shows what this is R value. So we have a real-time, what we call a virtual measurement in our software. So we're calculating R value in real time at every data point, and we can plot that versus tensile strain. And that's done at the top graph is showing you at a single point of measurement, and the bottom graph is the average 32 capability. So it's pretty obvious that since the y-axis is set to the same scaling, you can see there's much less variability on the data on the bottom. And in fact, there's almost 2.5 times less variability. And this is for mild steel. And then looking at 6000 series aluminum, same thing, that the top is a single point of transverse. The bottom is the average 32 capability. And again, the y-axis is the same scaling. And this shows almost 6.5 times less variability. And then finally, the 5000 series aluminum, which is known for having a large amount of PLC effect. And we can see that there's a very steppy pattern, sawtooth. And then at the bottom, that's what the average 32. Again, the y-axes are the same scaling, and there's almost 20 times less variability. So when I look at the top graph, if I was going to pick R value at, say, R15, which value, what would you say the R value is there? This kind of a big scatter. Whereas on the bottom, it's pretty clear. And as well as you don't, let's say R value of 0.6 was my minimum specification. We can see that none of them fall below there. Whereas here we have a large enough scatter where, could be 30% are below there at that point. So just want to share some customer comments that we've spoken to over the years. And just to let you know, you're not alone. I assume many of you might have similar concerns or comments. Operators' most hated words are, you need to retest this. Here in R&D, we just want the right answer. We never considered it could be variability in the test. The internal study found almost 30% variability, even in 6000 series aluminum. QC labs were testing 8 to 10 specimens, or until they got the right answer. We always cut 2 specimens now, just in case we have to retest. And last year, we completed 42,000 tests, requiring, and 20 to 30% of those required retesting. And by my math, that could be almost 12,000 tests per year. So what does poor repeatability cost you? Some of the questions that we started asking was, what's your pass criteria for R value? Typical answer would be 0.5. How often does your product fail? Well, it could be 15 to 30% of the time. What do you do when it fails? Of course, retest specimens, which brings on the follow-up question, what do you do when that retest fails? Is the material deemed to have bad R value results? What happens to the product? What's the effect on production? How often does this occur? And any idea on the cost of it, the money lost? And just to kind of give an example of one of the retest procedures we came across is that if so these are for specimens that had failed, and now they're retesting them, and they really just need to get one that passes, and then they can stop testing. So they test one, it fails. They test a second one, it passes. This gray area is where they stop. But if they continue testing, they might find that 5 of the next 6 pass. However, coil B from the same lot could be that first one fails, next one passes, and they stop there and ship the product. However, the next 5 of the 6 could have failed, and both of these products are considered the same at this point. So the idea is that average 32 eliminates retesting. The multiple transverse strain measurements eliminates variation in R value due to the PLC effect, and it brings it more in line with that sub 5% variance, more like you'll see from other material properties such as yield strength. It simply eliminates retesting. And the idea here is that it's not your material necessarily, it's not anything else in your test setup. It's simply the properties and other things happening in the material that just make it difficult to measure at a single point. It's just not fundamentally the best way to do it. So in summary, obviously new materials present challenges for formability testing, but they can be overcome. Average 32 provides more repeatable results for R value of sheet metal. It reduces the risk of meeting product specifications. It improves product confidence, improved reputation of supplier and their customer, elimination of retesting specimens, reduced test times, reducing waste, less production downtime. It reduces potential shipping delays and ultimately reduces costs. So thank you very much. And if anyone has any questions, we'd love to try and answer them now.
All right, thanks, Dan. Hi, everyone. This is Charlie Pryor, Applications Engineer at Instron. I've compiled a few questions that came in both before and during this webinar, so I think they'll have a good relevance to the audience here. First question is, how will the surface finish or edge preparation affect the results? So you should definitely still be preparing specimens in accordance to the standard that you're testing to. However, I will point out average 32 is fairly robust and it is able to measure specimens of various conditions, but definitely still be preparing them in accordance to the standard. Next question, does it have any effect on the axial strain measurement or will it measure that any differently? Answer here is no. The average 32 will still meet, or sorry, the AVE2 will still meet the same specifications for other standards in testing. The axial strain will not be affected when paired with average 32. Next question we have here. How recently did the new ISO 10113 come out with the new literature? So the new literature was added to ISO 10113 in the beginning of this year, which is making it a little bit more limited for options now. As you can see from what Dan touched on, as of right now, I think we are the only company that has a standard product abiding by the new literature of the standard. I would definitely recommend reviewing the most recent revision if you haven't already. So this one came in, is not directly related to the topic, but it's still a question I can try to answer here. So this customer has experienced some variability in E-modulus values during stainless steel testing, and they were just looking for a little guidance or help. So here, there are many things that can affect the variability of E-modulus values while testing. Some of which could be your data rate, alignment of the load string, alignment of the specimens themselves, and preparation, and then many more things. So, I would definitely recommend you reach out to our technical support team if you want some further troubleshooting support, and hopefully we can help mitigate that variability for you. Next question, can the R value be considered a constant during all the plastic deformation of the material? And this was specifically for high strength steel sheets, but the answer here is no, not really. On some lower grade steels, it stabilizes after the rate change and could be considered fairly constant up to uniform elongation. But on higher strength materials, there's much less plastic deformation, so it doesn't tend to stabilize to a constant during a tensile test. Also, again, in the new revision of ISO 10113, it does show some details on the settling effects of the specimen that can influence the R value during your test. So I would definitely recommend taking a look at the appendix of ISO 10113 if you want to learn a little bit more about that. Let's see. Next question we have here. Typically, an extensometer uses a gauge length of about 50 or 30 millimeters, depending on the standard. With the video extensometer now measuring 32 points along the length of the specimen, how does the system handle the influence of the radius where the strain seems to not be uniform? So to clarify here, The average 32 is measuring 32 points in between the gauge length used, which would come from the location of the axial marks applied to the specimen. So these 32 measurements are always equally spaced throughout that gauge length. So for example, if you had a 50 millimeter gauge length, so your markings were 50 millimeters apart, the average 32 will select 32 equally distant points between that 50 millimeters. Another one I have, so what is recommended for measuring Poisson's ratio? So for Poisson's ratio, I recommend our AutoX 750 biaxial extensometer or one of our transverse clip-on extensometers. Let's see, we got a bunch more coming in. So how to get average 32 installed, I would reach out to your local salesperson and discuss with them. If you already have an AVE2, you could be purchasing it separately, or you can also purchase a new AVE2 with it. But yeah, I recommend reaching out to your local salesperson and inquiring about it.
Yeah, I also noticed some people asking DIC related questions, so digital image correlation or other softwares. So this is not digital image correlation, which cannot be verified traceably. The average 32 can be verified as any other transverse extensometer, so it can be verified to a traceable standard. So you do not have to speckle the specimen, you don't have to put any marks on it at all, just the axial gauge length for the two dots, the top and bottom, and then the transverse takes everything and does it all for you.
Yeah, since someone was asking, do you need to spray the specimen? No, you do not. Not like as Damage is saying, it's not like the DIC. So you would only apply the two axial marks to your specimen to mark basically the gauge length, and then that's it.
And this is only for measuring R value, not for measuring the necking of the specimen.
Hi everyone, so Matt Spirate here. So I'm just going to answer a couple that I saw come in as well. Does R value, or does the dimension of specimens affect the R value? And yes, it does. Typically, if you're testing a ISO or a JIS or an ASTM size specimen, you can get different results in the R value. And then I can see another one here of how reliable are the test results when using a clip-on extensometer when compared with the video extensometer. So it depends on the material, as Dan explained earlier. If it's specifically this material with the PLC effect, then it would be significantly more reliable with the new average 32. But in general, they are very comparable. And then there was another question here with, sorry, so they said, sorry if I missed it, but they already have an AVE2, so they want to know how they can upgrade, as Charlie commented on. So yeah, reach out to your local Instron representative, but yes, it's a software update as long as you have the latest version of Blue Hill, and you can get the additional hardware, and the AVE2 will be able to now have the AVE average 32 feature.
Yeah, someone asked, can it go through glasses? Could you verify what you mean here? Are you talking about like human-like glasses for seeing, or are you talking about like a safety shield kind of thing? Like, are you worried about the safety of the actual light itself?
I can say that if your question is about asking it, testing through a chamber, we've primarily done testing just for ambient testing where R value is done. So we don't have any information on using it in a chamber. It's not recommended at this time. and that's specifically the average 32 feature.
And there's another question here about, are we aligned with the ASTM test protocol? Yes, this feature would meet the same as the existing ASTM E517 along with the new ISO standard. A lot of questions coming in. This is great.
Yeah, trying to read through.
Will the system be able to allocate and measure the necking, or is this just to address R value? This is just to address R value. So the necking of a material is much more unpredictable, and obviously this is mainly for sheet metal, but you'd have to obviously do the width and the thickness, which is currently not possible.
I did see that someone asked about is the improved contrast compensation available outside this new system? It's primarily used for the average 32 feature, but yes, I believe it is being used when you're just measuring axial dots or axial and transverse dots. That's still a capability, obviously for other types of materials. So the contrast will be improved. And then if the dots are lost, does the camera lose sight of the specimen edges too? If the dots are lost, the camera will basically transition the strain source to be the crosshead. So as we've always done, it handles it very well. So you never want anything going out of control or running away. So there's different things we can do there, but correct, it would basically stop recording both axial and transverse strain.
Yeah, one of the things, we got a couple questions coming in about like accuracy and like kind of like the other question comparison of a clip-on to the video extensometer. And I want to clarify, so the accuracy is still the same, and so these other, like the clip-ons and other extensometers they're still accurate and they still meet the classifications. But I think the main thing here is the average 32 is a more appropriate application and way of measuring the R value for these types of specimens. I think that's the way you should be looking at it. It's meant to reduce the variability in testing. It's just a more appropriate application for these materials. It's not necessarily more accurate, and it's not really meant to take away from other clip-ons for other type of materials.
It looks like someone else had also asked about if they already have an AVE2, how would they get this additional feature? And it's simply an upgrade to your existing system. So you don't need to get a new system or a new AVE2. We can add that to your existing system.
All right, guys, I think we're going to kind of wrap up the questions here. We might have a few others that we're going to take offline and answer individually. But I'm going to toss it back to Nick to kind of wrap everything up.
Okay, thanks, Charlie. So yeah, like Charlie said, we're gonna wrap things up, but before we go, I just want to mention a few quick notes. So I know a few of you were asking about the recording and slides, so I'll work with Dan on getting a copy of the slides that we can share. We're also gonna throw the recording from today up on YouTube, and then each of you will also receive a link to the recording and the slide deck. So just keep an eye out for that. That'll likely come over tomorrow. And then next week, I'm gonna be joined by Elaine Gordanoff, who's going to be providing an intro to Blue Hill Universal Software, which is going to be great for all of our new and occasional users that would like to gain a better understanding of the tools and the workflows. For that, you can sign up now on Instron.com. And with that said, I just want to thank Dan for presenting today. Matt and Charlie, thanks so much for all your help with questions, and thanks all of you for sending all your questions in and for spending this time with us. We really appreciate it. So stay healthy, everyone, and we hope to see you again next time.